Welcome to videos on data converters. In this video, we shall see R2R digital to analog converter. This is R2R ladder back network, the conceptual R2R ladder network. As you can see now, there are resistors of value R and 2R connected in a ladder fashion. So this is the resistance R, and we have a 2R resistance, and this is again R. This is 2R. So likewise, there is a alternate resistors of value R and 2R are connected in this fashion, and ultimately finally you can see there are two resistors of value 2R and 2R connected in parallel. It is necessary to observe that. So looking into the circuit from this side, the resistance is 2R. If you see from here, this 2R or 2R which are in parallel will become R. So that in series will become uh, that in series with this R will become again 2R. So from any point of the network, if you see from here it is 2R, if you see it from here towards the right side it is 2R. So from any point of so at the point from here also the resistance, if you see towards the right it is 2R. That means to say, suppose if you have a resistance, if you are connected a voltage of V reference here, the voltage at this point happens to be V reference by 2. So you may be wondering, how does that voltage at this node becomes V reference by 2? So we know that the resistance looking on to this node is uh, 2R in parallel with R. It is R here. This R in parallel with R will look like as 2R. So here from here it is 2R, and you have one more 2R resistance coming in parallel with that 2R. If you see from here it's again R. So this R plus another R will become 2R. Similarly, if you see from node 1, V1 towards the right hand side, the resistance is R. We have a resistance R here. We have a voltage source V reference. So it's like applying voltage source V reference between two resistors of resistance R and 2R in series. So naturally the voltage at V1 becomes half of V reference. So that's why it is V1 is given by V reference by 2. Now the voltage at V2 happens to be half of V1. So since V1 is V reference by 2, so naturally V2 is V reference by 4, because V2 is V1 by 2. Since V1 is V reference by 2, so we are going to have V2 half of V1, which is exactly 1/4 of V reference. Similarly, V3, suppose we consider this as V3, V3 will be half of V2. So since V2 is 1/4 of V reference, so then V3 becomes V reference by 8. So as you can carefully observe, the voltage at the nodes V1, V2, V3 is V reference by 2, V reference by 4, and V reference by 8, which is changing as per 2 power n. So here it is 2 power 1, here V reference by 2 power 2, here it is V reference by 2 power 3. So this is what is required for your DAC operation. Depending on whichever bit is high or low, you're supposed to get the output voltage as per its weight depending on the position of the bit. So with this concept we can actually move on to the actual R2R ladder. Using R2R ladder, how do we realize a DAC network? So this is the actual R2R ladder network. You can see we have a op-amp used as a non-inverting amplifier with gain as 1 plus R2 by R1. You can see this is the network what we are looking into. We have a 2R, R, 2R, R, and this ladder is connected, and this switch SW1 to SWN will be used to switch the input voltage from VH to VL. This VH can be VCC and VL can be 0, or this VL can be some other voltage also other than 0. So as you can see now, since this node is connected to this V plus, so this is B1, which is MSB, and the voltage, the bit which is connected to this switch will be the BN, that is the LSB. So let us take a specific example of 3-bit DAC. Here we are considering VTH as going back to the previous circuit. Now here we have considered VH as the V reference and VL as the ground voltage. And let me see how the connection of this looks like. So here this is again that non-inverting amplifier with a gain of 1 plus RF by R1. We have resistors of 2R, R, 2R, R, 2R, and as it was said in the previous circuit, we have 2R and 2R which are connected in parallel here. So this is what the connection is. Now this is the, depending on the bit position, it will be made to V reference or 0. So here also we have 3 switches corresponding to 3 bits, which is B1, B2, B3. If you want to apply 1, 0, 0, so then this is connected to 1 and these two are connected to 0, 0. You shall see what is the voltage coming at V1, and that will be amplified by 1 plus RF by R1. Now we shall take specific examples of different bit combinations and try to find out how does the analog voltage changes as per the digital input of B1, B2, B3. So we are specifically looking into different combinations of the input. So how much is the input voltage that will be applied to the non-inverting terminal of the op-amp. So that's what is interesting. So since the input combination here is 1, 0, 0, so we have made, this is the B1 position that is made V reference, B2 is made 0, B3 is also made 0, meaning these two are grounded. As you can see now, these two resistors are grounded and are in parallel, can be represented by its equivalent, that is R. We had an R over here, so which is coming in series with this, and this 2R is retained as it is, and this network is retained as it is here. You can see V reference is connected to 2R. There's a resistor. Now we are supposed to estimate what is the voltage V1 here. So what we have done is we have replaced this circuit by its equivalent resistance. These two R's into 2R, two resistors in parallel is being represented by a single equivalent resistance R. Now you can see these two resistors, which are R and R, which are coming in series, will become 2R. So that is again in parallel with this 2R resistance. So that's what we are seeing here. So there is 2R here, another 2R coming in parallel, that is connected in series with this resistor, which is R, and we are supposed to find out what is the voltage at V1, because this is the voltage that will be applied to the non-inverting terminal of the op-amp. Now as we know that, so these two resistors, which are 2R, 2R, which are in parallel, can be represented by a single resistor R, and it is grounded. And this 2R, 2R is again in series. Sorry, this R and this R are in series, so it will become again 2R. So we end up with this. So from this we can write this, and from this series combination of R and R, we can write it as 2R. Now we have a potential divider like situation. So there is a V reference and 2R and 2R resistors are connected. We are trying to estimate what is the voltage at V1. So naturally the voltage at V1 is exactly half of the V reference, because it is connected with two resistors of value 2R, 2R. So now with the combination of the input as B1 is equal to 1 and B2 0 and B3 0, we get the voltage at V1 as V reference by 2. Now this is ultimately used as the input voltage for the non-inverting amplifier. So the output voltage of the op-amp will be V1 into 1 plus RF by R1. So we know that V1 is equal to V reference by 2. So when V1 is equal to 1 and other two inputs are 0, 0, we get the output voltage as 1 plus Rf by R1 into V reference by 2. That is, this is the gain here. You can see it is exactly half of the V reference. So this is when bit B1 is 0 and B2 B3 are, sorry, B1 is 1 and B2 B3 are 0 0. We shall take up one more example where we have B2 is 1 and other two bits are 0 0. So that's what the combination that we have. So again, we'll estimate what is the value of V1 and that multiplied by the gain happens to be the output voltage. We have this B2 as 1 and the other two are grounded. As you know, these two are in parallel and that can be represented by a single resistor R here. Now this R and this R are in series, can be represented by 2R here. We have a 2R resistance, so this is the again 2R, we have a reference. Now looking into this node V2, from this node if you just see towards the right, we have 2R resistor and then there is a V reference connected. I can represent it by a V Thevenin and R Thevenin. So V Thevenin we going to have a reference voltage of V reference by 2 and R Thevenin will have a resistance of R. Now you can see we have a V reference by 2 as a source and we have this R and R connected in series. We have a 2R here and this will be represented by a 2R and 2R and there is a voltage source of V reference by 2. Naturally the voltage at V1 happens to be half of this VTH. Now, half of this VTH is nothing but V reference by 4. So for a combination of V1, V2, V3 which is 0, 1, 0, the voltage at V1 would be V reference by 4. Now we shall see the last combination where we have the B3 is 1. So you can see now B1 is 0, B2 is 0 and B3 is made 1. So under such condition, what is V1 we are looking into? So since this is 2R, 2R, looking from this node to the right side, the V Thevenin, R Thevenin are written here. So the V Thevenin at this point is V reference by 2. Similarly, the R Thevenin is the parallel combination of this 2R, 2R, which happens to be R here. Now we have the combination of these two resistors, which is R plus R happens to be 2R. Now looking into the network towards the right side, so again we can write the V Thevenin as V reference by this voltage divided by 2, that is V reference by 4, and R Thevenin is equal to R here. So we have this network again. Now you can see looking into the network here. So looking into the, suppose if you are look from here towards the right side, I'm going to have V Thevenin as V reference by 4 and R Thevenin as equal to R. So that's what we have here. So we are supposed to estimate the value of V1 here. If you actually see, now we have this is the circuit from the previous case. So we have this R plus R, it will become 2R and this is again 2R. The voltage at this point is half of this V reference by 4, which happens to be V reference by 8. So V1 is given by V reference by 4 into 4 divided by half. Why means because this is like a potential divider, having some voltage divided between two resistors of equal value will be half of this. Exactly, V1 is equal to V reference by 4 into half, so which happens to be V reference by 8. Meaning to say, suppose if the input combination is 0, 0, 1, you will get an output voltage V1 is equal to V reference by 8. So when V1 is equal to V reference by 8, so then output voltage is gain times V1 is the output voltage. We have seen in all the different combinations that if B1 is 1, we are going to have gain times V reference by 2. If B2 is 1, we will have gain times V reference by 4. If B3 is 1, we have gain times V reference by 8. So this is what is required for a DAC operation. So depending on the bit whichever is on, we are going to get the output voltage, which is a weighted version of V reference. that is V reference by 2, V reference by 4 or V reference by 8, it just goes on. So this way we can